Okay, it's time to start. Okay, so good afternoon or good evening, everyone. Welcome to the GEH 1036. Actually, I'm surprised to have seen so many people. But I'm sure on Friday that I'll see less. But okay, anyway, so this is the general education module. Can you see the dot? Okay, so the course is called Living with Mathematics, and this is the first lecture. Okay, let me introduce myself. This is my name, Yang Yue, and my office is at Mathematics Department, S17 0705. Here's my email, matyngy@nus.edu.sg. So MAT is mathematics, and this is my last name and initial. Okay, and my office telephone is this number. So if you have any comments or feedback or complaints, please call me, write to me, and so on and so forth. I guess I'll know at least some of you throughout the term. Okay. Okay. So here's a plan. So this is the first lesson. So I will give you a general introduction about this course, and then we are going to talk about something about money. We'll talk about interest and annuities. Okay. I don't know whether I'll finish everything or because, okay, we'll see. So, okay, so let's start from the most important thing, right? So many people care about this. So this is the grading policy. So your final grade is going to depend on two components. One is a midterm test or mid-semester test. The weightage is 30%. Okay. So I scheduled the midterm test at the Friday just before the break. After 6 weeks, we have a 1 week recess, right? So it is a Friday, February 22nd, during the lecture hour. But probably we'll find another room because you need to sit sort of not next to each other. So I'll announce the venue later, okay, after I arrange everything. So it is a closed book, but you can bring one help sheet, one piece of paper. You can write whatever you want to write. Okay. I've already received emails concerning about what happens if I have to represent Singapore on certain sports events or something like this. If you, for some reason, you cannot take the midterm test, we'll have a makeup test, but you must give me the valid reason, right? Like MC or some authorized letter saying you are representing Hall or you're representing whatever. Your friend's birthday is not a valid reason. Is this okay? So, the other component is a final exam. It's 70%, the same format. It's closed book, but you can bring one piece of paper to help you. Okay. So the date is on 27th April in the afternoon. It's a Saturday. You can find this on the internet, on the IVLE or other web pages. Is this clear? Is everything all right? Okay. So now lectures and webcasts. Again, lots of people ask me whether this is going to be webcasted. Yes. So, well, you can have dinner at this hour instead of coming to here. Okay. So it will be posted on the Lumi NUS or IVLE. But I'm new to the Lumi NUS, so if there's problems, please give me feedbacks. I don't know how it works, but I'm sure that if there's any problem, it will be solved very soon. Okay. Now, okay, so I don't care whether you come here or not, as long as you learn the stuff, right? But I do encourage you to, well, probably attend lectures or come to NUS. So the reason is not attending my lecture. So I think I have two reasons for encouraging you coming to NUS. So the first reason is a good university have a vibrant atmosphere, right? So you by interacting with other people, you learn a lot of things, right? So, okay, it doesn't mean you have to go to a specific lecture, but across the faculties, certainly you'll find something you are interested in, right? So just now I show you an advertisement. So it is a public lecture on mathematics. So this Thursday. So I'll show you the same advertisement during the break, okay? So for example, you have public lectures or you have, I don't know, there are lots of activities. So coming to the school is good. Another reason is maybe you are better than me. When I stay at home, I was often distracted by, I don't know, by food or by other things. If you come to school and taking a proper class, then you have to concentrate for a rather long time, right? So it's less distracted, more focused. So I think this is important for young people. Okay. So that's why I encourage you coming to school. Whether you attend my lecture doesn't matter. Okay. Okay. So also I hope you give me feedbacks because I don't know your background. So this module is for everybody. So people are coming from different faculties, right? So they have different background. So I don't know whether what I'm doing is right, whether you can follow or you don't follow. So do give me feedbacks. And if you have complaints, voice it early. Okay? So is this clear? Please stop me if you have questions. Okay, so there are some reference books. I think I'm going to use the first one. I'll choose more topics from the first one. So I have a copy here, and I'm sure you can find copies from your friends or from some website. So it was written by a colleague of mine who is now retired. So this was a standard textbook for this course for several years. Okay. And then there are topics outside this living with math. For example, today's topic coming from this reference book. You can find an electronic copy on NUS e-resources because we bought the Springer copyrights. Okay. So you can find things there. And also there's another reference book. This is not a name. This is a consortium of something. So it's a name for a collection, for a group of people. So they wrote a book for just like living with math for general purposes. So I think at some moment I'm going to choose some topic from there. But let me repeat, the main reference is the first one. And from time to time, maybe we'll pick some topics from the second and the third. Okay. For this one, I think now they have 9th edition. The copy I have is 6th edition, so I put it here. If you, I don't know, if you search for it online, or you may see newer editions. Okay. Other things about the course is you have weekly tutorials starting from week 3. I think you have bid for it already, right? So again, it doesn't count towards your final grade, but it will help you to understand the materials. I hope you attend the tutorials. And I will post the slides and tutorial problems on the standard website, IVLE or Lumia UX. Okay. All right? Okay. Okay, so this is the overview of the course. So according to our website, what we are going to do is this. So we are going to exhibit some simple mathematical ideas applicable in everyday life. So the mathematics is simple, but somehow it's related to daily life. Right? And then in the process, hopefully you'll gain an appreciation of beauty and power of mathematics. Okay, so this is our objective. And the topics are chosen from these things. So because we will have 1 lecture for midterm and probably another 2 lectures for holidays. So I'm not sure whether I'm able to cover everything. So probably we'll select 6 out of the 8. It depends on how far or how fast or how slow I'm doing this. Okay. So today we are going to talk about money, and then next week we'll probably talk about logic, and then there are some some other topics. We'll see. As time goes, we'll adjust. Okay. So that's the introduction. Now we start the lecture, lecture 1. Any questions? Okay, so if you don't have any question, let's start the first lecture. Okay, so let's start from an example, right? So so that we know what we are talking about, what kind of question we are talking about. So here's a question. Suppose you put $100 in a bank at 5% annual interest. How much do you have after, 100 years? Suppose, I guess you are going to live over 100, right? So because technology is developing so fast, and cancer can be cured, and you can change lots of things. Anyway, so now here's the question. So let me repeat. Suppose you put $100 in the bank at 5% annual interest. How much do you have after 100 years? Okay, so that's the question. Well, however, this question is not is ambiguous. In mathematics, we'll say it's not well defined because the ambiguity lies into the word interest. How the interest is calculated. Okay, so there are 2 ways. The interest can be calculated in the so-called simple way or compound way. So we have to make sure that in which sense we are talking about interest. Okay. So let's look at this simple interest first. Okay, so you know that the 5% interest means this, right? So after 1 year, you are going to get this $5 extra, right? That's your interest. Okay. Now, so you get $5 interest each year. Now the simple interest means this. Over 100 years, you just keep accumulate this $5. Every year you get $5. Okay, year 1, $5, year 2, $5, and so on and so forth. Okay, so after 100 years, you get, this $500 as your interest. Okay? So you will get 600 in total because you have 100 to start with, and you have $500 as interest. Now, so this is the simple way. Now, in real life, simple interest is seldom used. So this is, okay, so probably the reason is because after 1 year, you have this amount. And then the actual $5 should be considered as when you're calculating the interest for second year, right? Otherwise, you can take out and then redeposit. So in real life, actually nobody uses simple interest. Now, how about this compound interest? Is the difference big or small? Okay, so let's take a look. So now the second way of calculating interest is like this. So let's make an observation first. So if you have this amount, if you have S dollars at the start of the year, and then at the end of it, you will have this amount, right? You know this, right? So say just now S was 100. Now the amount you have will be 105, okay? So now suppose we do it in a compound way to calculate interest. So at the very beginning, I have $100. So after 1 year, okay, according to this, I'll have $105, okay? Now after 2 years, so here's now it makes a difference, right? So the second year, the interest will be calculated based on 105, right? It's a compound, okay? So if you do the math, it is 1.05 squared, right? You multiply it twice and times your original amount, okay? I guess you are very smart. You know what happens after 3 years. So this becomes 3, right? This 2 becomes 3, okay? And so on and so forth. So after 100 years, you'll get this amount. So this is 1.05 to the power of 100 and times the original deposit. So I hope the calculation is correct. If you have a calculator, please help me. Okay, so it turns out it's like 13,000. So the difference is huge, it's big. Okay. Is this okay? Is it clear? Clear? Okay. Okay, so now from now on, by default, if I only mention interest, it always means compound interest. Because as I said, in real life, people seldom use simple interest. Okay, so now this is the most important formula for today. Okay, so we are going to see the variation of this several times. Okay, so so let me read the proposition first. Proposition is like a mathematical statement. It's like a theorem or whatever. So it's an important mathematical statement. Okay, so if you invest $0 with an annual, to emphasize is compound interest, with an annual compound interest rate of alpha. Alpha is a rate like the 5% and so on and so forth. Okay, you will have this amount after n years. So what is amount? Okay, Cn denote the dollar, the amount of dollar you have after n years. So it was calculated in this way, right? So you have 1 plus alpha raised to the power of n times the initial amount you invest. For example, just now, the C0 was 100, and the alpha is 5%, right? So we calculate n is 100. So this is sort of an abstract version of the example. I guess this is a GEH module, so we don't want to prove this. Actually, there are some people from math department, right? You can prove this by mathematical induction or whatever, your favorite way to show it. But I think it's quite clear. right? So if you understand the example, you would understand this. Okay? Okay, so there's a remark on alpha. So alpha is the 5%. So alpha is not 5, it's 0.05, right? So you should be slightly, how to say, you pay some attention on the number alpha. So usually it's a small number. It's like 0.05 or 0.03 and so on and so forth. Okay? Now, so before we move on to the next slides, what will happen is we are going to I'm going to give you examples based on these propositions, right? So you notice in this proposition there are four, we call it parameters, or four numbers, four items. Okay, so the four items are C0, the amount of dollars you invest, and alpha, which is the interest rate, and n is the number of year, and then the amount of dollar you have after n years, which is Cn. So there are four parameters, right? They are related. They are related in this way. Okay, so the questions we are going to look at are all has this flavor. I'm going to give you three numbers out of these four parameters and ask you to figure out the fourth one. Okay, so let me repeat. So the typical questions we are going to see are to find the fourth parameter, assuming that we know the other three, right? Because here's an equation. If you know 3 out of 4 parameters, you are going to figure out the last one. Okay, so you'll see the examples. Okay. Okay, since this is the proposition of the day, so let me read it one more time, then say goodbye to this. Okay, so if you invest C0 with the interest rate alpha, you will have Cn, which is 1 plus alpha to the power of n times C0 dollars after n years. Okay. 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 So now let's start the first variation. So here's a question for you. So when will your fortune double in the above scenario? That is, the interest rate is 5%. So you deposit certain amount of money, and you ask, after how many years I will double my amount? Okay? So this is the question. Okay, so let's do it slowly. Right? So let's try to analyze what it says. Okay, so we need to find out n. Assuming we know that C0, alpha, and Cn, which is double amount of C0, right? Okay, so the meaning of double the fortune means you get 2 times the amount you had, right? So we need to find out the number of years, the n standing for number of years, assuming we know we have the initial capital, C0, interest rate alpha, and Cn we know is double the initial C0, okay? So in other words, we are looking for an n such that this equation holds, right? So you see this is the Cn, right? Cn now become doubling the C0. So we know alpha, we know C0 will be canceled. It doesn't matter. You can put a number if you want. So we are looking for the integer n. Okay. So in other words, we are looking for n so that n satisfies this equation. This is the natural log. You know you can take logarithmic on both sides, right? So a typical log was base 10, but in mathematics somehow they use the log base E is Euler constant. Anyway, so probably on your calculator or you can find this. So you all know log, right? You know log function. No? Okay, so the next time I'll say something about log function. Okay. Let me write it down. Okay. You know the base 10 log, right? This is, you don't know any log. Okay, never mind. So okay, so now assuming you know, okay, so you take log on both sides, and the log function has this interesting property that it turns product into sum, turns power into product, right? So that's why we take log. Okay, so okay. Next time I'll say some property about log, then you'll see that by taking log, you get this equation. Okay? So once you get this equation, we can solve n. So, so here are some mathematical facts. So when x is small, this log applied to 1 plus x is, this means approximately or roughly x. So this is a math, I label it called math fact. So all math fact will be explained. So let's first move on and take this as a black box. And at the next lecture, I'm going to explain this, assuming you don't know it. Okay. I'm sure that lots of people know it, but anyway, so I'm going to explain all these things next time. Okay, so the log function has this property that log of 1 plus x is almost just like x. Okay, so assuming x is small. Okay. So therefore, when alpha is small, for example, alpha is 5%, right? So you can calculate n is more or less just log 2 divided by this alpha. Okay, so and then you look at your table or use calculator, you find out the natural log on 2 is actually 0.6, this figure. Okay, so multiply by 100, you get more or less this. So n is more or less this number divided by beta. In our case, beta is 5. Okay, is this all right? Okay, so now this 69.3 is lousy, right? It's not good. It's not easy to work with. People in bank somehow round it up, not for 70, but they round it up to 72. Why? Because 72 has lots of factors. It's easy to divide. Right? For example, 6 or 4 or 3 and 2, and so you get lots of divisors. So somehow they choose this. So in other words, so let's replace this by 72. The people in according to the reference book, people in the bank have this rule of 72. It says this: at annual interest rate of beta percent, it will take about 72 over beta years to double your fortune. Okay, so suppose beta is 2, then you get 36, right? Suppose, and you can calculate. So this is a rough estimation. Okay. Well, so there are lots of things you can replace investment to debts, but that's too bad, right? We want to have more positive things. Before I move on to the next slide, is the first example clear? Modulo the log. Okay. Is this all right? Okay, so let's move on. So here, I want to make an observation I want to compare the simple interest and the compound interest. Okay, so this is something called linear versus exponential growth. Okay. So this is a general fact. So let's recall the different growth of investment ft after time t under a simple interest versus a compound interest. For simple interest, it's just, it can be calculated in this, like something like this. Okay? So this is called linear because if you draw the curve, it turns out to be a line, right? So so this is a linear function. So this is called linear growth in t, right? But for compound, the formula is like this. So it's some number multiply like 1 plus something to the power of t, right? Just now we see 1 plus alpha to the power of 100. So it's something like this function is called exponential function. So the growth this is called exponential growth. Usually the c is bigger than 1. If c is less than 1, then you go down to 0 very quickly. But if c is bigger than 1, it increases quite fast. Okay. So another mathematical fact is exponential growth is much faster than linear growth. This probably, many of you know this. People from computer science probably care about complexity and so on and so forth. From mathematics, again, I think you know this fact. But anyway, so this is a fact we are going to use. I'm going to explain this fact on Friday. Okay, so now let's look at another variation, right? So we are going to do lots of examples based on the proposition of the day. Okay, so the second variation is okay. So it's like a quarterly rate, or okay. So sometimes interest rates are presented on a monthly or quarterly or semi-annual base. Okay, for example, let's see this. So consider a loan of amount C with an interest rate of 2%, compounded quarterly. So it's not an annual rate, but a quarterly rate. So every year you have 4 quarters. Okay, so how much do you own after 1 year? Is the question clear? So now we calculate, you are given the interest rate, not an annual rate, but a quarterly rate. Okay. Okay, so, well, it's easy to make mistakes. So, so the wrong answer is just because it's quarterly, you just multiply 4, right? So it's something like this. Okay, but we don't spend time on wrong answers. So the correct answer is this. Because the way of the compound interest, right? So we know the formula. This is from the proposition of the day. So you know that actually the correct answer will be 1 plus alpha to the power of n. Now n is 4 because every year has 4 quarters. So you'll get actually this amount. Okay? So the conclusion is such a loan has annual interest rate of 8.24. Okay, rather than 8%. So this rate is often called whatever, APR. I'm not a financial person, so probably in the bank there's a special name for this. Okay, so is an example right? Okay, so now let's look at the same problem but from different angle. So just now we know the quarterly rate, we want to find the annual rate. How about the other way? If I know the annual rate, can I find out the quarterly rate or monthly rate? So here's an example. So if a loan has an annual interest rate of I, I is like 5% or 12% or something like this, what is the monthly rate alpha? Is it clear, the question? Okay. Okay, so the solution is just the same proposition. We use it one more time, right? So alpha and I are related by this formula, right? So 1 plus alpha to the power 12, because every year have 12 months, right? So will be equal to 1 plus I. This is the annual rate. So in other words, 1 plus alpha is you take the root, 12th root of, on both sides you get this, and you subtract 1, you get the monthly rate. Okay. This is a remark probably from the textbook, but so it says, okay, I'll just read it. I don't know how important this. Okay, so in principle, the amount you own should increase by a factor of 1 plus alpha each month, with alpha related to I as above, as this. So, so that the amount increases by a factor of 1 plus I after each year, right? So this is just a restatement of this relation. Now, however, I don't know, probably people in the bank always give us some false information or whatever. So it's not uncommon for a bank to interpret the monthly interest rate to be I divided by 12. So the effective annual rate actually is higher. Okay, so for those people from math department, you have to show this, right? Why this is true. But anyway, so this is just a remark. It's not important. Okay, so more examples. Okay. Here's a problem for you. So you are given two options. Invest 1,000 now, or take this amount, 1,100 in 2 years' time. Now the question for you is, what annual rate of investment returns, what rate alpha would make the first option more attractive than the second? Okay. You have 1,000 to invest, right? The option 1 is just invest now. Okay. You know certain rate, alpha. Okay? You have two options. One is investing now. The second option is you don't invest, but you for some reason just take this amount in 2 years' time. Okay, so the question for you is which one is better? Which option is better? Okay. Am I clear with this? Okay. Okay, so let's work out the solution. Again, it's the same formula over and over again. Okay, so under option 1, in other words, we are going to invest now, you will have this amount after 2 years, right? We have seen this many times, right? This 2 is n, is a number of years, right? So you have this amount after 2 years. So the question becomes, for which alpha, this guy is bigger than the 1,100, right? So this will be the return of the first option. The right-hand side is the return of the second option. So we certainly want to have better return. So this is the mathematical way of saying this question. Okay. Now somehow if you press your calculator, you get this. So if alpha is bigger than this amount, then it is good. For example, it's 5%, then you should choose the first option. If it's 4%, probably you choose the second. Okay? Okay. Questions? Okay, so we can reformulate the question as this. So what is 1,100 in 2 years, in 2 years' time, worth today? Right, so you know the sort of the inflation so this is a same problem, but we look at it from different angle. Okay, so so more generally, we can do this. So what is having X amount in K years' time worth today? So for example, here X is the 1,100, K is 2, right? So in future you'll have certain amount, and what is that amount of money worth today? Okay. Assuming you know the rate of investment return is I, like 5% or 4%. So, in terms of the proposition, we want to find C0, assuming we know alpha n and Cn. Is it correct, right? Because Cn will be the amount of money you have after n years, right? So you know Cn, you know the number of years, you know the interest rate, which is the I, and then you want to find out what is it worth now. Okay, so this is the same proposition with a different variation. Okay, so here's the solution. It's the same thing. Okay, so the solution is suppose you have amount y, you have y dollars today. This will grow to the same formula, right? 1 plus the interest rate to the power of k is the number of years, times y in k year time. Okay, so if you set x to be this number, and then you want to know what is y, right? So we see that x amount of dollar in k years time is equivalent to this amount of dollar now. Okay, so the formula is y is equal to x divided by 1 plus I to the power of k. Okay. So, so this is a solution. So the y is called present value of x in k years time, assuming the interest rate is I. Okay. Is this clear? Okay. Now this is almost like repeating the question. So here, say you are offered the amount of S1, S2, SR at future years T1, T2, TR, right? So, I don't know, some insurance company talk to you, right? Say, after 2 years, you are going to get S1. After 3 years, you're going to get S2. After, I don't know, 20 years, you are going to get SR. Okay. So you are offered these amount at the future years, these years. Okay. So, and assuming the annual interest rate is I, you know the interest rate, how much is that equivalent to you getting today? Right. So what is the present value of these problems? Well, you know that just now we have seen this formula. So the present value of SI given at year TI is this, right? Just now we saw this formula. So it's the future amount divided by 1 plus I to the number of years. Okay? So in today's money, the offer is equivalent to, you just add them up, right? It's equivalent to this. Okay, I won't read this, but you know. Okay? Now, in mathematics, there is a way to write this long sum in shorthands. I guess if this is the first time you saw it, you probably need a few seconds to adjust. But for people who have seen it, this is really convenient. Okay, so the shorthand is this. So sigma is probably sigma is a Greek letter for S, for sum. Okay. So sigma, and then this I equal 1 means you start from 1. And then you end with R, right? So when I equal 1, I goes from 1 to R. So when I equal 1, you get this term, S1 over something. When I equal 2, you get the second term, S2 equals something. And all the way to this variable, R. So the last term will be SR over something, right? So this is the shorthand for this sum. Okay, so here is the typical definition in mathematics. So here's a convention. So in general, suppose you have a sum of n terms, like a1 plus a2 plus dot 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 plus an. The shorthand for this sum is as before, right? So you have a sum. This is a symbol for sum. The first term is 1. The last term is n. And then you change the I from the first term all the way to the last term, right? So this is, you start from A1, and then you increment I by 1. So you get A2, and so on and so forth, all the way until you hit n. Right? So this is the shorthand for this sum. We are going to use this because otherwise there are lots of typing. Okay, so let's see one example. So for example, this, the sum of k equals 0 to 12, x to the power of k. So this is a shorthand for a sum. We start from x to the power of 0. Okay, by the way, the convention is anything to the power of 0 is 1. Okay. And then you increase the k by 1. So you get x to the power of 1. You get 1 plus x. And then you increase one more time. So you get x to the power of 2. So the k equal 2, all the way until k equal 12. So this stands for the sum of 1 plus x squared plus all the way to x to the power of 12. Okay? So this is an example of geometric series. Again, I assume most of you have seen it before. Okay. May not be in the sum form, but this series. Okay. So now we are going to look at a rather complicated example. Maybe I'll take a break now, and then after the break, we'll see this. This will take 7 slides or something. So let's take a short break, like 5 minutes break. Okay, and then I'll come back to this. So here, this Thursday at LT 31, which is at Science, there will be a public lecture. It's called Mathematics in Solar Systems. So the speaker will be a big shot in the field, and currently we have a workshop at Institute of Mathematical Sciences. Usually there are some famous people coming, and the institute will ask them to give lectures for general audiences, not for specialists. So there's a series. Okay, so this is one of the current one. This is the current one. This coming Thursday. So if you have time, please attend the public lecture. So this is an example of, I'm saying the university life is lively. So it's probably you'll get something in return for coming to university rather than stay at home. Okay, so well, so that's the advertisement. Now back to business. Just now, some people asked me whether I can upload the slides before the lecture. So because I think I have lots of mistakes, so maybe by going through the lecture, I'll get some feedback, I'll correct mistake, and then I'll upload. So this is my plan. But if you all prefer to have it beforehand, and then I can upload, but and then I'll make changes and upload it again. So I don't know. So let me know your preference. Okay, it's just, for me, it's both ways are okay. All right, so back to business. So here's the maybe more complicated problem. Okay, so let's do it slowly. Okay, here's the problem. So it's a mortgage problem. So you borrowed this amount, right, $100,000 at this annual rate, 6%. Now, to be paid monthly over 25 years, right? So you borrow this amount, and then you are going to return to the bank every month, okay, in over 25 years. Okay, so now we need to calculate, so how much is your monthly payment, right? We need to calculate what is the amount you have to pay back every month. And also, how much do you own after a certain amount, like 15 years? Right, so here's the problem, right? So you borrow money, and then you are going to return it every month over 25 years. So we need to calculate what is the correct amount you should pay back. And at certain amount of year in future, how much do you still own? Okay, so this is actually a problem from real life, right? Okay. All right, so in general, okay, so this is an abstract version for this. Suppose you borrow C dollar at annual rate I, and then you pay monthly over N years. How much is your monthly payment R, right? So in the example, C is this 100,000, the I is 6%, the year is N equal 25. We need to calculate what is R. Okay, so here. So in problem 2, you have this parameter. We are asked to figure out what is this R, which is the monthly payment. Okay, so you are clear, right? Okay, so let's solve the problem slowly, one component, component by component. Okay. So first, let's find out the equivalent monthly interest rate alpha. Right, so we are given the annual interest rate. Now because we are going to return money in monthly basis, so let's find out what is the equivalent rate, monthly rate. Okay, so note that the monthly rate alpha satisfies this. We have seen this many times, right? I don't need to explain. So you can solve it. Now, in our case, 1 plus alpha to the power 12 is 1.06 because I is 6%. So you have this equation. It's easy to solve alpha. Even you don't know log, you can still solve it by taking the 12th root, right? So you get this. This is roughly this number. Okay, so we know the monthly rate alpha. Okay. Okay, so then let C sub k denote the amount owned at the end of the after k months. Right. So you are going to every month you are going to return some money, but you also own a little bit more. So you want to know after k months what is the amount you are still own. Okay. So C0 is at the very beginning you have C, you borrowed C dollars. So after 1 month, you still own what? With the interest, you own this amount to the bank, right? C0 times this 1 plus the interest, monthly interest. But however, you paid back R dollars. So after 1 month, C1 is this part minus subtract R. This is okay, right? So you own this amount, but you already paid R. R is your monthly payment, so therefore you have to deduct R from this number. Okay, so it's simple, but let's make sure we understand simple things. Okay, after another month, that is at the end of the second month, what do you own? So you have C2. So the amount of you own C1, right, at the end of first month, becomes 1 plus alpha times C1, right? And then you paid another R. You paid $R back for the second month. So you have to subtract R, right? Now you simplify. So C1 is there. So you replace C1 by this amount. So it's 1 plus alpha times, in the square bracket is C1, is this, right? So the minus R is minus R, so you get this. Now you simplify. So this is 1 plus alpha squared. C0 is C. So it's C times 1 plus alpha squared. Subtract this R times 1 plus alpha, and this minus R is there. Okay, so this is after second month. Then you know, right? So after third month, do the same, and so on and so forth. So continue. In general, after K months, you own this, because at the beginning of K months, you own this amount. Now with the interest rate, you own a little bit more. It's 1 plus alpha times this. But you made another payment, so you take away R. So this is a recurrence relation, right? So it's like CK is equal to 1 plus alpha times CK minus 1, then subtract R. Okay, so if you understand what's happening after 2 months, you understand this. Okay, so let's again try to simplify this CK. Okay, so we can do something like this, but probably some of you are very good at math. You can do it the other ways, but let's just see. This is convincing. Okay, so CK is this, right? This is the recurrence relation, so I copy it. Now, what is CK minus 1? Now, you can apply this equation to CK minus 1. So CK minus 1 actually is 1 plus alpha times C sub K minus 2, right? And then take away R. So this is similar, like from going from 2 to 1. Okay. So you get this. And just like before, you get this relation. And then let's observe the pattern, right? You see every time you sort of take away 1K, take away 1 unit from the subscript, and you raise the power to the same one, right? So, and also every time the power of R increase, right? Originally is 1 plus alpha to the power 0, and then you add 1 plus alpha to the power 1. The next round you have 1 plus alpha times to the power 2, and so on and so forth, right? So you can work it out. Maybe you can work one more step and see more evidence of the pattern. But we don't have too much time, so if you keep doing this, in the end, you are going to move everything here to the power. So you get 1 plus alpha to the power K times C0, which is your original loan. And then minus R times, now this is the sum. This is a shorthand for J equals 0 is this term, J equal 1 is this term, and then J equal 2, you get the next term, right? So on and so forth. In the end, you all the way to the J, the last term will be to the power K minus 1. So C sub K is this. So this is the amount you own after K months. Okay. If you can't follow, can't read on screen, I'm sure on a piece of paper you can figure it out. It's not hard. Okay, so we are going to calculate the sum. So we need to have a formula, right? So that formula is this. So the sum of the geometric series, like the sum from J equals 0 all the way to K minus 1, x to the power of J, So we know that this is a shorthand for this. It turns out the formula is a fraction, is 1 minus x to the power k divided by 1 minus x. We are going to show this on Friday. Probably most of you know this, but never mind. We are going to prove it again. Okay. Is this okay? So this is the sum of the geometric series. There's a formula. The formula goes like this. Okay. Now, what we are interested in is x is 1 plus alpha. Right, remember here. We want to calculate sum. The x now is 1 plus alpha. Okay. So if you apply it to x equal 1 plus alpha, you get, on the top, you get 1 minus bracket 1 plus alpha to the power of k. At the bottom, this 1 minus bracket 1 plus alpha. So you get a minus alpha here. Okay? So this is the sum here. Okay. So now if you replace this term to the funny sum, you get this one. So I swapped okay. So here I have a minus, but if I swap it, the 2 minus cancel out. So you get this. Right. So C sub k actually can be written in this way. Is this all right? So just some calculation. Okay. Okay. So the next step is, so after the loan is fully repaid, after n years, in other words, after 12 n months, we own 0 amount to the bank, right? So C sub 12 times n is 0, because after n years, you don't own anything to the bank. So this is the equation we have. C sub 12n is 0. Okay, so plug in the k equal 12n. So you get this equation. So you have this equation, so this is the C sub 12n. Okay. So this is 0. So we know C, we know n, we know alpha, we want to figure out r. Okay. So by easy calculation, right? So you multiply alpha on both sides, then you divide it, you can move the negative term to the left and divide this guy. It's very easy to get. So you get R equal this. I won't read this, but you know, right? So is this okay? So this is the correct amount you should pay every month to the bank. Okay, so now back to the concrete example. So in problem 2, so we have this C is 100,000, I is 6%, alpha is, we calculate this, right? Alpha is this amount, N is 25 years. So you can use this formula, but plug in this. Or alternatively, you can use this, because 1 plus alpha to the power 12 is equal to 1 plus I, right? We know the relation between monthly rate and the annual rate. So you can simplify a little bit. You can change this. You can replace 1 plus alpha to the 12 by this. But however, the alpha is still useful because there's alpha here. You cannot get rid of. Right? So it depends. You can use this formula. You can use this formula. It's the same. Okay. So after you plug in the numbers and punch your calculator, you get R is more or less this. Okay, so the actual number, we don't care, right? So you can get the correct amount. Okay? And there's another question, right? So how much do you own after 15 years? Right? To work out the amount owned after 15 years, so we have to use the proposition again, or the formula. So we know that the amount after k months is this C sub k. So it is given in this way. So you plug in the numbers. So after 15 years is this, 180 months. So, so you know every number on the right-hand side, right? You know C, you know alpha, you know R. We just calculate R, and you can do this. You can simplify a little bit. You can simplify this 1 plus alpha to the 12 as 1 plus I. So you, but more or less it's the same thing. Okay, so this solved the problem 2. Okay, I don't know how do you feel whether this is easy or complicated. But for me, this is new to me because I don't know how to calculate these things. Only because I have to teach you, and I read at this. So indeed, this illustrates the objective, right? So the mathematics behind are very simple. So this is the proposition we use over and over again. But somehow it is useful in real life, right? So that's what we are going to do in the remaining of the semester, right? Okay. Any questions? Are you still with me? Or? Yes. Good. Okay. Now let's look at the same thing, right, with a little bit more twist. So this is something called annuities, right? I don't know the meaning of the word, so I look at Wikipedia. So it says this: an annuity is a series of payments made at equal intervals, right? So the examples of annuities are regular deposit to a saving account, or monthly home mortgage payment, or monthly insurance payment, and pension like CPF, right? So this is, so the problem 2, the example we just saw is an example of these annuities because that's sort of like a mortgage, right? Now we are going to, okay, so mortgage is one example. Now we are going to look at another example. So this example is relevant because it's sort of like, it's related to CPF. So let's look at the next example. So here's a scenario. So when you retire, you may give a sum of money or the principal C to CPF, to the CPF board, okay? And in exchange for receiving a monthly income for the rest of your life. Right, so you have some money at CPF, and then every month you withdraw money from CPF until you die. Okay. Now, this is the mirror image of the mortgage, and the same mathematics applies, right? So, for example, okay, so why it is a mirror image? So now you are playing the role of the bank, right? You loan this amount to the CPF. And then you get monthly repayment, right? So just now you own money, you pay back to the bank. Now you have money, then you withdraw, right? So this is a mirror image, but it's not exactly the same. There are 2 important differences. Okay, so first, you do not determine the interest rate I. The CPF does. Right? Just now, you know the rate. So now you don't control the rate. The other party control the rate. And also another difference is the repayment lasts for the rest of your life, and you cannot predict it. Right? You rather than fix a period of n years, right? You don't know when somewhere call you and then you die. Okay, so there are 2 differences. So let's see how CPF solve the problem, and they can tell you the correct amount or the reasonable amount you are going to get from the CPF. Is this all right? The setting. Okay. Good. So the question now is, how does CPF decide? Well, the answer actually is simple and quite reasonable. So first, because CPF doesn't know, he is not a fortune teller. Like he doesn't know when you die, right? But he knows the average life expectancy, right? So he can use the average life expectancy as a rough gauge of n, right? Because the average lifespan is this amount. So somebody maybe live longer, somebody live shorter, and then they balance out. So the CPF will use the average lifespan for this n. Okay, it's reasonable, right? For example, if the retirement age is, I don't know, maybe this is, okay, let's say it's 62. And the life expectancy is 85. So the CPF will expect the repayment period will be 23 years. Okay, so, and then how does CPF determine the number I? Then the CPF will do his own investment, right? So he has an estimate of the return of the investment. So the CPF board analyzes its various investment to see what sort of annual interest rate I it can afford, right? So he will determine the rate I. So these two items actually give us two important parameters, right? The n and the I. Okay. So after this, the CPF will determine the monthly repayment, use the formula we just spent 7 slides to develop. It's the same thing. Okay. So after you know the n and the I, then you can use the same formula to determine what is the payment, monthly payment. Okay. So it is this. So the C is the initial amount, the alpha is the monthly rate, the N is the year, or you can use the I, which is the annual rate, the same thing. Okay? Okay, so let's look at the example related to this retirement. Okay, so on your retirement, you have a lump sum like 200,000 to provide an income until you die. Okay. So the CPF estimate that you will live for another 20 years, 20 extra years, and assumes it can earn 4% on the capital you give to it. So what amount would you expect to receive each year? Wait a minute. Sorry. Okay, so here's the mistake that what I calculate is each month. Sorry, I have to correct it. That's why. Okay. Anyway, so sorry. Okay, here is the example, right? So we are going to have an example in terms of retirement, in terms of CPF. Okay, here's the setting. I will not read it again, but this is the setting. So now let's follow our formula to get the result. Okay. So we have this. We have C is 200,000, I is 4%, and N is 20. Right. So these parameters are there. So as before, we will find the monthly rate corresponding to this annual rate. So the calculation is done in this way, and somehow it is this number. And then the monthly return is this, right? So then you get, each year you just multiply this by 12. This is the amount you get each year. Is this okay? Okay. Okay, so this is the last example of today. Okay. So now here's another example, phrase in a different setting, right? So it's about saving plans. So now consider the retirement saving plans of twins and Beth, so A and B, right? And Beth. So they choose different plans. Okay, so Anne saves amount of A at the beginning of each year for 40 years. Now, her twin Beth somehow is more lazy, so she starts 20 years later and save B amount each year for 20 years. Okay, so Anne choose the first option, Beth choose the second option. Okay. So in order for Beth to have the same amount of retirement savings as Anne, when they retire in 40 years, because they are twins, so they retire at the same age. How much more must Beth save, assuming that their saving grows at the same annual rate, 3%? Okay, so the annual rate is 3%. Now, Anne choose the first option, pay this amount for 40 years, and Beth will choose pay the B amount for 20 years, right? So now we have to decide how much more Beth must save, okay, in order to have the same retirement money. Okay, so now let's do some mathematics. So let Y sub k denote the amount of money N has at the end of year k. Right? After k years, N has this amount. Okay. So then what we have is this. So okay, at the beginning is 0, and after 1 year, N saves $8, but the interest rate is I, so after first year, N will have this amount, A times 1 plus I, right? Now, after second year, so the N already has Y1, amount of Y1 in the bank. She paid another $8, right? $8 is the annual payment. So N pays another $8. So you have this amount, multiply the interest. You say, okay, so at the beginning of the year, N already have Y1 in the bank, and then he pay another $8. So at the beginning of the year, N has this amount in the bank. So after 1 year, with the interest, N will have this amount. Correct? Right? Okay. So if you simplify, you get this one. So you multiply anyway. So it's very easy. Now, let's do one more to see the pattern. Right? So after another year, again, at the beginning of the third year, she already have Y2 and another portion of the payment, $8. So she has this at the beginning of the year. After 1 year, she will get this. So if you simplify, you'll get that. Okay, so now you see the pattern. So in general, after k years, you have yk equal a times. Now here the pattern is you start from 1 plus L to the power 1 and 2 and 3, right? So in general, you from j equal 1 all the way to k, right? So this is the pattern. So after k years, you have N will have this amount. Okay. So we know the formula, how to calculate the sum of geometric series. So you get this amount. So this is I, it's not 1. Okay, so you get this. Okay. Now let's compare the other plan, right? So after 40 years, N has this amount, right? Because you plug in a number. I is 3%, so you get this 1 plus I is 1.03, right? And then the rest are the same. You just plug in, you get this number. Okay. Now, similarly, you do the same calculation for Beth. So she will have the amount of B times this thing, but now she pays only for 20 years. So what she has is this. At the end of this period, Bess will have this amount. Okay? So now, if these two are equal, so you have an equation that this amount is the same as this, right? So just draw a big equality between them. You get B over A is roughly like this. So you can simplify this and get this. Now, according to the calculator, is more or less 3. So Bess has to pay much more, right? So the lesson is you better start your retirement now, right? You are still young, right? I'm too late, so you can do it, okay? So I guess that's the first lecture. So next time I'll have 1 or 2 more examples, and then we'll explain what is log and how to add the geometric series, and so on and so forth. Okay. Don't forget to give me your feedbacks, including those who are just watching webcasts, right? So do give me feedbacks. Okay. And okay, so that's it. Thank you.